Hi, in this example, we're going to look at first law applied in rigid tank. So let's write down what's given. So given is rigid tank, so volume is constant, and it's 1 cubic feet. So now we know it's in English unit. And the T1 is -20, and the quality 27.7. So we know it's a mixture. Then it's heated, then reach up the temperature as 100 Fahrenheit. They want us to find the heat transfer, find the Q. So in that situation, we're gonna review what we said about if it is a constant volume. Our first law equation is heat transfer Q is equal to delta U plus work hours, and there's no work hours, so our equation will be just Q equal to delta U. So in order to find this heat transfer, we just need to find internal energy change. In order to do that, first we're going to look at state 1. At state 1, they give us two things. They give it's a mixture, give us quality. So our V1 is going to be equal to VF plus X VFG. And oops. Okay, so we're going to look at the exam. We're going to look at the table. This is at -20 Fahrenheit. At -20 Fahrenheit, we're not going to use A11. We're not going to use this because this is going to be in the English unit. All right, so here we're going to look at -20 Fahrenheit. Again, make sure you look at the English unit. And I have to confess, I have already recorded this one later on down the road, realized I was looking at the matrix system. So here I'm having a do-over. So make sure you are looking at matrix system for this time. So -20 Fahrenheit, and we're gonna figure out the U, right? So UF will be 6.019. And UFG will be 85.874. So bring that here. Oh, here I'm actually calculating V. Yes, we do, because the second property, at stage 2, you have temperature 100 Fahrenheit, but you need the second property. Where that second property coming from? Coming from V1. So V1 is required to calculate it as well as U1. So we start with V1 then. VF from the table is 0.01156, and then X is 0.277. That's a quality. Our VFG is going to be VG minus our VF. Okay, from here we can calculate our V1. Let's pause, see what we got. So the calculator give us 0.933, and the unit here is going to be cubic feet per pound mass because it's in matrix in English system. Then we also know we need to find our internal energy U1 as well. U1 is equal to UF plus X UFG. From the same table, which is table A11E, at -20 Fahrenheit, our UF is 6.019. I'll show you right here. It's 6.019, and UFG is 85.874. And the quality is 277, and this will be 85.874. Put into calculator, let's see what we have. So the answer is 29.806, and the unit for that will be BTU, British Thermal Unit, per pound mass. That's our U1. Okay, so now we're going to move on to the state 2. As you predicted earlier, for state 2, you need the second property, which you already have. it's V2, since V2 equal to V1, being a rigid vessel, constant volume. And the second property, which is given, it is T2 as 100 Fahrenheit. So knowing this two, our goal is to find our U2. So for state 2, we don't really know what state that is. So let's go to table A11E and the temperature table as at 100 Fahrenheit. Our goal is trying to compare the given or the calculated V with VF and VG, right? So let's see, at 100 Fahrenheit, this is our VF and the VG. Our VF is 0.01386 and our VG is 0.34. And do you realize our V is way greater, since our V is greater than the VG. This VG at 100 Fahrenheit is 0.34045 cubic feet per pound mass. So that's telling us this is a superheated vapor. So we're going to go to the right table. So what table will we go to? We're going to look at table A13E, right? So at table A13E, we know it's 100 Fahrenheit, and we need to look at the second property. Okay, so right here at 100 Fahrenheit, the second property is specific volume 0.933. All right, and we don't know the pressure, so we don't really know which table we're gonna go for. But this is, I'm glad actually this problem give us this opportunity to look at it. Let's see, at 100 Fahrenheit, and our V is, this one is 5.8165, this one is 3.85, so it's way greater than ours. So I'm gonna scroll down and see if it's getting close. This 100 here is 1.8, ours is 0.933. So remember this value here, 0.933. Okay, so here it's getting close. At this 100, my volume here is 0.90, and at this one here, this value is cannot see, it's 1.1043. So it's between those two values. Then that's where we're gonna get this information from. Okay. And so what information I want to get it? What's my ultimate goal? I want to find U2, internal energy at state 2. So I'm going to look at, this is my U column, this is my V column. My goal is getting this value out, right? I'm actually going to see. So my goal is getting those values extracted out. So in order to solve U2, we're at table A13E now, since it's superheated, and we're going to use linear interpolation across the table and only take out useful information, since we know V and we want to find U. And we find V that is wrapping up this 0.933. The first value is 1.1043. The corresponding U is 111.55, right? And then next, it's going to be this 100 Fahrenheit, and the corresponding V is 0.9072, and corresponding U is 111.16. It's pretty close, those two values. But what we're trying to calculate? We're trying to calculate 0.933. So we're going to use the linear interpolation to do that. We can go ahead using delta U over delta V. So the answer for that will be 111.16 minus 111.55. This minus that. Then in order to do that, we're going to have corresponding V difference. Once we have that, we're going to use this unknown U we're trying to figure it out. For example, I'm going to use U, this U minus 111.16. Then correspondingly, my V will be 0.933 minus 0.9072. Alright, so we'll go ahead and calculate, see what we got for this U2. So with calculation, we got U2 as 111.21. Well, that's about right? We don't have to in between those two values, and that's what we have. So the unit here is going to be BTU per pound mass, and that's going to be our U2. So I'm going to go back to the real screen. Now let's look at what we have so far. We got our U1. We also calculate our U2. In order to figure out our U2, we first have to figure out V1 first. Since V2 is equal to V1, then we did the evaluation, realized it's superheated vapor, and based on in the superheated vapor, based on the specific volume, we need to find our U. So we find those 2V that is close to 0.933, and we linear interpolate the U. Now, knowing U1 and U2, remember going back to our Galvani equation, to find a heat transfer, we just need to find the delta U. Then we can figure out the last step. Q is basically equal to delta U. And here I'm going to use, theoretically it's big U, right, because internal energy. So in that situation, you're going to times mass. And I think the mass is given for this problem or not. All right, they didn't give us the mass, so we need to figure it out. So it's m times delta U. And now let's take a look. It's going to be U2 minus U1. U2 we just calculate as 111.21. And our U1 is this value, 29.806. Alright, and that's in units of BTU per pound mass. Then we need to figure out the mass. Alright, I'm glad actually we need to do that. How do we find the mass? Find mass in thermo is quite easy. Why? Because we know mass is density times volume, right? The mass is a constant, regardless state 1 and state 2, they are the same. So the density of 1 times the volume of there, and the density we know it's reciprocal of specific volume, then times volume big V. Then in thermodynamics, in order to find the mass, it's big V over small v. This is volume, this is specific volume. So knowing that, we can find it. Now let's take a look. For state 1, do we know the big volume? We do, because it's a rigid tank. It's 1 cubic feet. And in state 1, our specific volume we calculated is 0.933. So regardless if you are using state 1 or state 2, you're going to have the same volume and same specific volume. You're going to get the mass, so it doesn't matter. Now let's put in a calculator to see what we got. So with calculation, we got this mass as 1.072 pound mass. So knowing that, we can bring back to this final answer here. The heat transfer is going to be equal to mass 1.072 pound mass times 111.21 minus 29.806. BTU per pound mass. That will give us the unit for the heat transfer as BTU. Let's pause, see what we got. So final answer I have here is 87.25 pound mass. All right. All right, so I got 87.25 and I look at the answer is 84.7. I know there's something I did wrong. So I went back and checked my V, the first step, finding the specific volume for step 1. The numbers all here are right. However, the calculation here is wrong. So with that change being 0.962, and my U1 does not need to be changed, what would be done would be the cascade to the next mistake will be here because V2 is equal to V1, and then however, this does not change. It is superheated vapor. Why? Because this is way greater than 0.34, still superheated vapor, so still going to be A13E. However, this changes the linear interpolation. It does not change too much because the difference between U here are similar. So we got 111.2684. It's not much difference, but really difference is going to be mass, because the mass is big V over small v, and the small v here is 0.962 instead of 0.933. That's 1.04. So with the correct mass, with correct U1, and I got 84.7. So it's humbling experience, and hopefully through this you will know mistake happened, just need to go back to correct it, and we move on. All right, thank you so much. Sorry for taking you to the wrong detour a little bit earlier. Okay, see you next time. Bye.